Welcome to today's webinar. The topic today is response spectrum analysis optimization to achieve effective modal mass. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Thomas Eichner will be the presenter today. He is responsible for the development of the dynamic add-ons, and he works also in the customer support team. Okay, then I say some words how you can ask questions. At first, I switch off my webcam that you can see the full screen. Just press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Thomas. Thomas, it's your turn.
So, thank you, Andreas, for your introduction, and also a hearty welcome from my side. I'm glad you're all participating in today's webinar on dynamic analysis, and I would say we will just jump into today's content. So for today, you can see it on the right side here. We will investigate structures containing several members. And the goal of the webinar is to find the least amount of modes to use for the response spectrum analysis in such models. Of course, whenever there is a plenty amount of members within a system, there can also occur like local eigenmodes. We can see that on the bottom right figure here. Those eigenforms won't take effect on our response spectrum analysis, and so we do not need to treat them. And so let's start with how we're gonna proceed through this problem. So first, we will give an overview over the features and the add-ons within the dynamics part of the program. Then we will continue with the model on the top right side. I will briefly explain the model itself and also describe the investigation we try to make. Well, the investigation will be to reach the effective modal mass most efficiently. Then the next step is to perform the response spectrum analysis on that truss model. This we will follow up by the reduction of the amount of the eigenforms within the modal analysis, and we will also select the suitable eigenforms within the response spectrum analysis. In the end, I will also go over the second example, which is shown on the right bottom side, and we will also get another trick for reaching less eigenmodes for that model. So I would say we will start with the overview here. So we have the basic add-on, which is the modal analysis. The modal analysis describes the calculation of so-called eigenforms, which is the structural response to dynamic behavior. And the modal analysis is used for each other add-on. So each other add-on does need the modal analysis as well. For the response spectrum analysis, well, it just takes the eigenforms out of the modal analysis and creates a state of the structure according to the mode and the used acceleration within the response spectrum. This is done for each mode, and with the standard combination rules, those modes are combined to find the final internal forces, which then can be used for the design. So the pushover analysis, well, it also uses the modal analysis, since it, well, basically we consider a structure, and the structure is now being pushed from one side with an increased loading. And the distribution of that loading is giving according to code with, there are different shapes, for example, a rectangular shape, a triangular shape, and also a modal shape. So we need the modal distribution to create that loading. The pushover analysis itself, it's mainly used for retrofitting structures. So when you imagine a structure being built several years ago, plenty years ago, and it already endured an earthquake, and now you want to see, okay, where do I have to go? Where do I have to look for like problematic beams which could have yielded or could have been destroyed during the earthquake. So the main purpose is to find the weak points of the structure to make it easier to retrofit those exact points. The last add-on we have, and it's basically the most complex one, well, at least for the theory, because the time history analysis, it is calculating the dynamic equation directly. So we can do it by either, well, simplifying this equation process with the linear model solver, which uses the model analysis, or we can use the more exact solver, which would be the Newmark solver in our case. Okay. Also, maybe the time history analysis is not earthquake only, so it's used as well as the model analysis. It's not earthquake only, but it can be used, for example, for vibration designs, for general investigation of the structure and its behavior. And you can also see on that right figure here, in the last webinar, I performed a time history analysis on a footbridge and investigated on the acceleration limits. So one last add-on that needs a honorable mention here is the building model. With the building model, it is possible to define stories. And while we define the stories, the program also automatically produces result lines and shear forces in walls and so on. With that result line, for example, we can easily inspect the total shear force for the earthquake excitation. So also a good speed up for some work. Then I would say we are through with this introduction, and then we would just start into our first model of today. So here it is. We can see our columns. We have here 8 times 9 meters in the in the length. And we have 50 or 60 centimeters times 60 centimeters columns here. Those columns will get smaller on top. And this top structure is mainly a truss structure in one direction. So we see in the X direction, we have these trusses here. They also are all trusses in this direction. Let's go here. We see it. We have these truss sections right here. In the other direction, we don't have these trusses. So I would estimate this to be less stiff. And we can inspect the members which are in the Y direction as well, because I planned them differently. In this case, I gave them the beam member type and I added some hinges for the rotational degrees. So we will have the Y and Z rotation free in both ends, and additionally we will have the rotation about its own axis only free on one side. Because if we would place it free on both sides, the system would just get unstable because the member could rotate around itself. So that's about the structural, the structural, not behavior, but the structure type here. We also have some loading. We have some dead loads, which we will inspect right here. It's really simplified to just some member loads on the one hand side on the top of this roof structure, as well as on the bottom part of this roof structure. So in total there are 30 kilonewton per meter in each of those rows. And the same is also applied for the live loads, which I just simplified to be 10 kilonewton per meters on the top side as well as on the bottom side. So, and now we are at the perfect start for the dynamic analysis. So the first thing is we have our model finished, we have our loading finished. We maybe also made some design already for the structural limit state. And now we want to just add the earthquake design to the structure. And now I will guide you through that procedure. We will just start by going into our add-ons. That's always the first step to take. We will go into the add-ons tab, and there we will go for our dynamic analysis. So since the modal analysis is always needed for one of the others, we can spare a click here. I will just go for the response spectrum analysis. Modal analysis is checked automatically as well. Then we can check for our standards. And yes, we will just go for the German annex. The whole webinar works the same for different annexes as well as different standards there, because the main difference in selecting something here is the response spectrum and not the analysis procedure. So we will go with the Eurocode and we will click OK here. Then we will see that we have added our modal analysis settings, spectral analysis settings, as well as our dynamic loads. And with that, we can start up. One thing we need for dynamics is always the masses, since in the dynamic equation, we have also the masses. So we need to define them. For that, well, in general, we try to define the masses to be as precise as possible for the situation in which that earthquake would happen. So the Eurocode, for example, gives us some combination rules to achieve this. And those combination rules, we will just use them for the automatic generation. So we will go for our design situations, and there we will pick our seismic mass combination. For that, I will pick our combination wizard load combinations, which means now we have the automatic created. And if we now go for load combinations, we will see just the combination created. And this is the one we will use for our dynamic analysis as our masses. So now we can go into our load cases, create a new load case of name modal analysis. I'm just gonna rename it here. And we will pick our masses, which we just created. We will go into our modal analysis settings, just for you to see what we are going here first. Well, pretty much I will go for the root method of solving, since we will use that also later on for some automatics. And so I want to have it comparable in general. On the right side, we won't do anything yet. We will pick the consistent mass matrix and all directions will be active. So nothing too special here. We will press OK and continue with our response spectrum analysis. So within the response spectrum analysis, well, we almost always need to consider accidental torsion. So I will just directly activate it here, 5%. That's the way to go. We will go for response spectrum right here. And we can quickly look inside. There we have an AGR value of 0.6. We have a ground type AR. If you're interested on how to pick those input values, we do have our snow and wind and seismic load maps, which can be seen right here. With that, you would be able to just click somewhere here and find your acceleration value right there. Also, as soon as you switch to the subsoil class, which is here, we can also find our subsoil class. Okay, so we won't go into we won't take like a specific site here. We just go for the standard values, which leads us to a nice 1 meter per square second peak acceleration. Also, if you're interested in those values in the gravity domain, we do now also have the toggle to switch between the visualization of a percentage of G or the absolute values. The same also applies for the tables. So now that's easily transferable. Okay. When that's done, we see we have the X and Y direction. That's here already finished. So the last thing would be to also give the results to our design add-on in the end. And this can be done by creating a new design situation. Let's go for the seismic situation in this case. And there it is. We will have to select something else here. If we rewind ourselves on the response spectrum analysis, we do work with results only, not with loads. That means we can't use these load combinations. We will need to use these result combinations. And therefore, it needs to be created because it's not automatically created by the program. So whenever you do this, you will look out to create a result combinations generator. With that done, we can select it for a seismic design situation and also see the outcome right here. There it is. We have our dead loads combined with our live loads as well as with the earthquake loads. Okay, so that's it for that. I would say for the modal analysis, that's the root. That's perfectly fine. Now we will just go for calculate all. And let's see what we get out there. So now it's done. We got our 4 eigenfrequencies. Of course, there won't be enough. We have a fast calculation. We can look into our effective modal masses. And with that effective modal masses, we will see for the X direction, for example, we still don't have any mass participation at all. So that means we will need to increase our amount of modes. And now there would be several options. And now we will look at them right here. Let's delete this one and copy that. From that copied one, I will just switch it to the automatic to reach effective modal mass factors. So this would be our first setting. Let's call it all. And with all, I will reference to this mass matrix setting since we did select everything right here. Okay, for the next step, we will go for another one. And within that, we will deactivate the Z direction as well as the rotations around the X and Y direction. And this is gonna be our XY MTZ. So we reduced, within that setting, we reduced the mass matrix to only be in the directions of our investigated earthquake. We did select the X direction and the Y direction within the response spectrum analysis. That means we will have to consider the X and Y direction here. And also, a bit depending on the torsional stiffness of the building, and also in X and Y direction, there's also the rotation around the Z axis. So that's like for the torsional modes here. Okay, for settings, we won't do anything here because we don't have to neglect masses. Just as a hint, if you have like a grounding plate, then it is needed to neglect the masses there. Because if you won't neglect the masses of a supported surface, the program most probably will never reach the effective modal mass. Since the plate can just won't move. I mean, it's fixed on the ground, so it won't have any modes except for how do I say that? Like computational stiffness results. That means if you have a fixed support, it's not completely fixed. It's something like 10 to the power of 12, and therefore there would be modes also for the plates, but they wouldn't be usable. So the tip is here, if you have grounding plates, you would neglect the masses. So now let's get back to the topic. We have now two modal analyses, one with the whole setup and one reduced one to only fit to our loading direction. With that done, we can select the all here, and I'm also gonna do a copy paste of those two. For the top one, for the modal analysis now, for the second one, we will pick the X, Y, and Z settings. And for the last response spectrum, we will pick our lowest case 5, so our new modal analysis. And now we will have something to compare. And for that, we will now have to calculate it. And I won't let it calculate through here since it takes a few minutes for the results to be there. So we will just jump into the calculated file. So within the calculated file, it's pretty the same. It's just with the results. And what we want to see here is the results from the modal analysis. So let's look at that here. Now we are looking at this precise modal analysis, which was with all mass matrix entries, and we will see kind of 367 modes, where some modes are really like only local modes in that case. So we will have to reduce those. We will also see in the effective modal mass tab that we have tons of modes which just don't have any effective modal mass here. So they could be neglected in general. Okay, so let's compare it to our second one. As a reminder, we have 367 modes here. We will go for our modal analysis X, Y, and Z. And there we will see we reduced the amount of modes drastically. We only are left with 70 modes here. So the mass matrix settings are one way to drastically reduce your eigenforms. Also, if you like to have some more speed within the modal analysis, we also have the possibility to change to the diagonal matrix here. Well, it's not as precise as the consistent matrix, but we also have to reconsider we are working in the earthquake field within the response spectrum analysis, and there are lots of uncertainties. And if you compare that all to, for example, Pendelschlagversuch, it's like if you test windows, there you would go and let a tire fall against that window, and that's called the German Pendelschlagversuch. So within that Pendelschlagversuch, we would carry out a time history analysis, a nonlinear time history analysis, and each time step and each result is extremely important. So for such analysis types, the consistent matrix is needed. But for like earthquake design, we can always think about using the simpler diagonal matrix. Okay, so we will stay with the consistent one. And yes, maybe one more hint here. We have further options. We can also go for the modal analysis to be carried out within a frequency range. So for example, you could go and search for natural frequencies above 15 Hertz and below 17 Hertz. Let's just do this for a second. We will just select this one, this one modal analysis settings. The rest can be same, and we will just calculate that one. And the biggest benefit is that it's really faster if you know your region of frequencies you're investigating, because you don't have to calculate all the previous frequencies in that case. Now we got it, and we can look at the natural frequencies there. We see perfectly fine. We got all the frequencies between 15 and 17 Hertz. So with that, you can construct your own like system of modes here. Okay, so another thing is, and therefore I'm gonna deactivate the results there, go into our frame model, and we will look at our finite element mesh. What you see now is that we have multiple finite element points here on every beam member. Now, there can be one eigenform per degree of mass freedom. That's how I call them. For example, this finite element point. With our mass matrix definition, this point could move to the x direction by 1. And that would be one mode. It could be moved to the y direction by 1. That's another mode. And it could rotate around the z-axis. That's the third mode. So for each of these points, we have theoretically 3 possible modes. And that means we can reduce our amount of modes if we reduce our amounts of mesh nodes here. And for those systems, we can just go for our calculation here. We can go into our mesh settings and go into our members. And within that, we can see that we have, well, here a division of 10 for special types of members. This field is also used for the checkbox below. We see this one. It says activate member divisions for second order and large deformation analysis, structural stability, dynamic analysis, imperfections, initial strain, and so on. So with this checkbox, we will activate the split also for the dynamic analysis. And I'm gonna take it simple. I'm gonna just pick one here. I'm gonna let this option on. That's perfectly fine. And with that, we will get rid of our plenty in between FE mesh nodes. It's also to be said, as you can see, only the beam members have those mesh nodes. The truss members do not. So internally in the program, we implemented already to simplify those truss members by 2 points, since it's just not needed to have more, also for static analysis. Okay, let's see. I'm not gonna save it. I have the results of that exact file also right here. Let's see, we have here the one with one split. Before we switch, I just wanna have a last look on our X, Y, Z modes. So we had 79 modes in this case. Now we will switch to our one FE mode model, and there we will go again for the X, Y, Z, and there we will see we reduced our modes by almost a half again. So in contrary to having about 360 modes, we finally have a better countable number of 35 modes. And that's pretty nice. So we can go with the calculation from that on. Now, let's see. We do have the response spectrum analysis of all here already carried out. So that means with the whole mass matrix. We also have the response spectrum analysis carried out with the reduced mass matrix. All the other settings are pretty much the same. And now we can go and look at our results, since it's also important that our results do match with those simplifications. And with that, we will just go for the maximum displacement. We can see it about 6 millimeter. And if I just switch here between my response spectrum analysis, it's pretty much the same deformation figure, and it's also the same 6 millimeters. That's well, for rough test, I would conclude the results to be equal in that both analysis. Okay, so now we have our model reduced. We have our eigenforms reduced. What I did not mention yet is the selection of the eigenmodes within the response spectrum. Because in general, we will go with the simplified one. In general, if we go for the selection of modes, this won't be on and just everything will be selected. So this would lead to 35 modes that need to be calculated. But since there are lots of zero modes, we can further reduce them here. We will just go for an effective mass ratio. We will neglect all the ones which are, let's say, that's some testing, all below 2%, and we will still be over 90% in the y direction, so that's possible. And with that, we will lose again like 2/3 of our eigenforms. What do we have left? 1, 2, 3, 4, 5, 6, 7 modes. We're left with 7 modes within the simplified one. What would be with the exact one? here we see it. I also adjusted it here, and we have about, okay, I counted them before. They are roughly about 20. So again, quite a lot more than in our simplified variant. Okay, so we have that. Now we will also go for the last performance setting, how I call it. Well, and it's within our spectral analysis settings, we have the option to save the results of all selected mode shapes. I almost always do it. It's gonna increase the calculation time because it also has to save everything in each calculation. And it will also produce bigger files, since you will have all the nodal and member results for each mode available. So the thing with this is you would use it with, let's say, up to 20 or 50 modes, but if you exceed those amounts, I would not save them. You should only save them if you really want to inspect them. Else how it's just yeah, too much, not too much data, but unneeded data storage. Okay, so now we are through with this model. The last thing on that model I want to show you is just the interaction with our design modules. So there within the input data, we can go for the ultimate limit state. We have it defined, we have it to design. We have here the accidental one. We can also go for the ULS one. Then we will get the ULS checks performed. We will just calculate it. And there it is. I only inserted that one column for the checks, but as you can see, the results are just possible to be overtaken into our design add-ons as well. Okay. So then we will jump right into the second model. Let's see, I have it right there. And now we have Truss Hall. In that case, we have pretty much a block used here. If you did not see the blocks before, I will just briefly show them to you. When we click on this top left button here, we will directly navigate into our block manager, and there are several examples of buildings. And for today's webinar, I oriented myself on our truss systems. So there are lots of examples which you could use for your structure. As well as let's look into our flat truss system. So there are also more complex systems already pre-built. And further, we can go into the curved ones. And well, here's exactly the model I am using in the background. So the only thing you would have to do when you select such a block, let's see into the guided user interface there. Well, the main point would be to still adjust our members. So for example, here there's all with our reinforced concrete ones. We can change them and also directly see the changes which are now in the model. I did that all already for our system, so we can just jump into our real model again, and we will see we have some trusses in between in diagonals. We have some, and the rest are mainly HEB 120. And exactly, so that's the system we will inspect now. Now we can go for our loading. And with the loading, it will be pretty clear what I'm trying to show in the end. Here we have our uniform loading. I made it really simple. I just placed member loads on each member in this case. We have a total loading. Let's see the results again. Right here of 585 kilonewton with this distributed loading. And in the next variant, I created a load case also with 585 kilonewton in total. But instead of having them distributed over the beams, we did concentrate single mass loads right here. So for your information, you can create such mass loads just by changing the load type into mass. And with that, we can just place them as any other node as well. So I did it already for all the nodes here, and now we have the equal system with two different loading approaches, and we will just go for the investigation of our mode shapes there. So now we will go for our modal analysis with our distributed load. And we will just jump into the settings so you are also up to date on what we did perform right there. We did the simplified ones, so we did the X and Y direction as well as the rotation about the Z axis. And we did use the distributed load, and that's it. For the other modal analysis, we just picked the masses differently. There we just picked this concentrated mass on nodes definition. Okay, so now we will go. We have our distributed modal analysis, and we will see about 548 modes right there within the effective modal masses. Well, we see here a region. It looks pretty useless to me because it's almost zero at the most part, and it's pretty low. So I would say those are way too many modes to treat. And now let's compare it to this different modal approach where we concentrated the loads. And there we go, we reduced the modes by a factor of 10. So maybe also for your information, what we did here is we went with our member divisions of 10. We would achieve a similar effect as in the other model if we also would decrease this number of intersections to 1. Okay, one benefit of our mass definition here is that we really directly place our masses, and within the response spectrum analysis with accidental torsion, the program will automatically generate torsional moments, and that at every place where masses are. That means at members, for example, that are, let's say, modeled as with two hinges and they are not really torsional stiff, they will have a torsional moment in them. And with that direct definition of the masses, we can force the program to make our torsional moments on that point. So that's another benefit of this modeling approach. Okay, so that's it for this one. Now we can go for our last one, and that's the load case 6 in that case, because we can also go on our response spectrum analysis results, of course. And within that, we can go for our results. And well, now we see here the 4 millimeters and pretty much nice model now. Let's see into our distributed load one. We can also go for the results here. And there we will get the problem where we have tons and tons of response spectrum analysis load cases carried out. So we will not wait for this now. Just as a hint, we have this multiple processor functions. So there will be several carried out at once. Nevertheless, those will just be too many to be done in a fast time. So the reductions of the modes should always be carried out. So let's go for the final conclusion here. So when we treat a trust model just like this, where we have tons of members and we do want to carry out a response spectrum analysis, then we can get into the problem of too many eigenforms very fast. And the possibilities to reduce these eigenforms are: we do adjust our modal analysis settings, we do adjust our directions here, we do adjust also our mass matrix if wanted. We can go for the diagonal one. We do also want to neglect masses which are supported. We want to neglect surface masses if they are a ground plate. And okay, the next thing is we can go for our mesh settings. And reduce our member divisions to 1. And the last and the approach that is linked to the most work in the end is to directly define your masses wherever you want to have them. So those are all the possibilities for you to reduce the eigenforms. You can also use our special functions in the modal analysis to find frequencies above a frequency or below a frequency. This can also help in such situations, but they are suited only for very special cases. And so you would have to decide on your own which procedure would fit you best. Okay. Well, then we are already done with today's webinar, and we will just jump into our presentation again. And I would say that's all from my side. I hope this whole topic was interesting for you and you have learned something from it, and I wish you a nice day. So see you. Bye-bye.
Thank you, Thomas, for your presentation. I have a hint for you. You can get the add-on steel joints at a reduced price. Until the end of the month is the offer valid, and you can get 21% off. For more information, just click at the button on the bottom here, or you can scan the QR code. Okay, that's also all from my side. I thank you for your attention. Thanks to Thomas for the presentation. I wish all a nice rest of the day. Bye-bye.